Hello everyone, and we're going to continue to talk about more detail on some of the unconstrained optimization algorithm, such as the classic BFGS quasi-Newton method and conjugate gradient method with Newton's iteration and some other ones. And later part of this lectures, we're going to review again some of the linear and nonlinear constraints for optimization and the corresponding algorithm. Okay, so this lecture meant to be give you a more detail or more depth insight and about these each one of the optimization algorithm. Like we again, we still using the Rosenblock functions as one of our test functions for optimization, and we see how each one of the algorithm perform in that case. The first classic unconstrained optimization algorithm is the quasi-Newton method BFGS algorithm. The BFGS stands for Boydens, Fletchers, Goldfarb, and Shannon, and most of them are from Stanford University. And they developed this algorithm for the purpose is not using the entire Hessian each iteration to invert. So they're using a so-called rank 2 update and trying to approximate the inverse of a Hessian each iteration. We have a detailed discussion on this algorithm in the textbook and all our lectures on chapter 8, and so I'm not going to spend too much time on the algorithm itself, and instead we'll show you how we can easily using the BFGS method, and which is the most common algorithm used today in many applications, such as the time series analysis and kernels methods and other so-called machine learning and data analytics algorithm. And the BFGS method is a little bit more so-called computational demanding, but however, his performance is really well over the year, being tested more than thousands or hundred thousands of applications. That still stands very well. So we're going to use the Rosenblock function in this lecture, still talking about how these methods can be easily applied. First, we demonstrate the Rosenblock functions as his first derivative. This is for Rosenblock function has n different variables instead of just 2, as we illustrated previously. Okay, and for the special case of a 2-dimensional, we can easily write it out like that. Okay, so we already have it defined. Because the Rosenblock function is a famous function or popular function people use to evaluate their optimization algorithm, and so we're going to continue study using this. And the SciPy.optimize library has this Rosenblock function already defined. SciPy.optimize library has a Rosenblock function itself called Rosen, and the first derivative of a Rosenblock function and second derivative, and we have also the Hessian product information. We show you in this lectures, including the cosegment to how to calculate the multi-dimensional, multi-variable Rosenblock functions, but we can just simply import it directly from SciPy. For other functions, may not be so lucky. You have to explicitly find those. Okay. And you're going to ask me what are usually the popular test function for nonlinear and linear and constraint optimization. There is a so-called Wikipedia page you can refer to. And this page is called Test Function for Optimization. It lists all kinds of some of the function actually popular for testing your optimization algorithms. Baylor function, Goldstein price function, and boost function, and one of those, let me see, there is one pretty popular as well, called egg holder function. So its shape is almost like an egg holder you have in the in the grocery store. Macroeconomics function also very popular, and some of our research article using these functions to test our our new development on optimization algorithm recently. So going back to our main flow, and this is how the first derivative of a Rosenblock function was used, and I just call it Rosenblock derivative. And solving this function is really simple. It just gives you a initial solution, or initial guess, using the minimize function from the SciPy.optimize, and the method specified is BFGS. Specify the Jacobian information is using the Rosenblock derivative. And I'm using an option equals to true, so it shows all the solution result altogether. Okay, so just one line you can do this. Majority of effort is using, if you're not using the Rosenblock function, you just have to define your function derivative, and so on and so forth. And one line of code can be used to solve your problem. Then I print out the result. It gives you the current Hessian inverse using the BFGS. This is the objective functions is 10 to negative 14, so it's practical 0. Optimization terminate successfully, and the solution is 1, 1, 1, 1, 1. The BFGS method apparently using 26 iteration, using the 30 functional evaluation, using 30 of the Jacobian evaluation. Okay. Next, we already talked about this algorithm before called Newton-Conjugate algorithm. It's just using a second order Taylor expansion approximation of the original algorithm, and we solve a system of linear equation H inverse times the gradient of f at the current. So in this case, for the Newton's conjugate gradient method, I need to specify a Hessian information. So here I listed for the 5-dimensional problem we have on hand, how to calculate his second derivative. Okay. And this is a Hessian matrix for 5 different variables. And it's kind of a banded symmetric matrix with banded diagonal. Again, the Hessian of a Rosenblock function can be calculated like this in terms of routine. I can also directly import the Rosenblock function Hessian from the SciPy.optimize library. So you can use either way. And then we're just using the Newton's conjugate gradient method, given the first derivative and Hessian information. Okay. And I specified the convergence tolerance for x is 10 to the negative 8, and display equals to true, so I want to display all the output. So this is basically what we get, okay? Compared to the previous example, taking about takes about 48 milliseconds right here for the BFGS. The Newton-Conjugate gradient method actually took much less time, about 13 milliseconds. So significantly faster and less computational effort to solve this problem. I'm sorry, it takes about 11 milliseconds. So significantly less information needed. Another way to defining the Hessian is for Hessian product information. For example, for large minimization problem, storing the entire Hessian matrix may not be memory and time efficient. So the Newton CG conjugate gradient method only needs the product of the Hessian. Basically means I only need the Hessian times the PP is direction, basically, for any type of calculation. As a result, user can supply the code, his own code, to calculate this product rather than have to store the entire Hessian information. And this issues usually take Hessian is symmetric, like we showed, is banded symmetric positive definite method if it's the original function is convex. So we can usually just store its so-called upper part of a Cholesky factorization. Or if this is not symmetric, we can store this so-called LR factorization or SVD factorization. So it's significantly save the memory in this case. And we can define a function called HP, h of xp, basically, is a series of function. How these functions define for Rosenblock function is right here, represented right here. So give you each one of the dimension, and this is just a vector, but it's a vector of function, okay? And this is so-called Rosenblock Hessian with a product, which is basically x and p, and we give a Hessian function within. So it return a value. And it will return a value if you supply with the x current solution and the p vector, okay? So this is much easier in that sense. We can using, actually, in fact, Rosenblock Hessian function with a product. This function is already defined in the SciPy.optimize library. So we can just simply apply this into the minimize subroutine Rosen function, initial guess method using Newton conjugate gradient, the Jacobian function information. This parameter, instead of using Hessian, we call it Hesp. Hesp is this is so-called Hessian product function. Okay, the rest of them is the same. This actually takes slightly longer to calculate and to solve the problem. Is there 11 millisecond? It's a 16 millisecond. So for Rosenblock function, doesn't matter which one is using because the solution time for these two options are similar. However, for a large-scale problem, using the so-called Hessian product may be a little more efficient in that case. So Newton's CG method is more suitable for solving larger-scale problems in that sense. However, Newton-Conjugate gradient algorithm can be somehow has approved convergences if the Hessian information is ill-conditioned. Okay, and therefore it provides a ill-conditioned so-called search directions. So the search direction may not be very reliable. Very minor numerical error could cause the function to the algorithm to converge very slow. So here is the rectified method, and stands for truss region Newton-Conjugate gradient method. It's also part of the Python optimized library. The only thing is when he solved for these quadratic quadratic program actually has a bound on this on how far the p can move, the direction times the step size can move. So give a truss region for that. Simple as that. So we show you how this is going to be used as well. For this function, doesn't matter, and the Hessian function is well conditioned and close to optimal solution. This method only takes about 14 milliseconds, and the behavior is very similar to Newton-Conjugate gradient method, and is since the truss region is not very effective too far. It takes about 24 seconds as opposed 24 iteration. Sorry, takes about 23 iteration instead of 26 iteration. Number of functional evaluation only using 24 instead of 33. But it does take a little bit more time on solving, evaluate the Hessian information in that sense. Okay. Again, this truss region Newton-Conjugate gradient method can also using the Hessian product information for solving the problem. So I give you some of the references for these information, these algorithms, truss region problems, using truss region subproblems, and so on and so forth. These are the two very famous references in that range, and for this topic. The next algorithm we talk about is the truss region near exact. We'll call it truss region exact. The method we talk about so-called Newton's conjugate gradient method, truss region, Newton-Conjugate gradient method, truss region, Krylov are suitable for solving large-scale problems and problem with thousands of variables, and they are well tested over the years. And that is because the conjugate gradient is really reliable for approximately solving the so-called trust region problem. So since only the product of the Hessian will, and of an arbitrary vector is needed, we just need to do a rank 1 or rank 2 operation. And so this is especially suitable for dealing with a sparse Hessian. Sparse Hessian, just like the one we have before, what I call a sparse Hessian. Let me show you. This matrix, Hessian matrix, it's only have the diagonal and the one line off diagonal has value. The rest of the matrix are 0. If this matrix getting large and majority of the parts is are 0 elements, so this is what we call the sparse information matrix. So for medium-sized problems, and the storage and factorization cost is non-critical in that case, so it is possible to obtain a solution with a few iterations by solving trust region subproblem almost exactly using Newton method. So this is trust region exact Newton method is suitable for medium-sized problems, such and usually we perform 3 or 4 so-called Cholesky factorization for the Hessian matrix, and therefore we can solve the problem with a less number of iterations. So we're going to show you this using the trust region exact Newton method instead of using the conjugate gradient method to solve the system of linear equation. What I mean the linear equation is, let me go up. And equation 2, correct, is equals to the system of linear equations, basically the Hessian inverse times the gradient. All right. Sorry, I have to switch back and forth on explaining what I meant. So we're using the same method and almost the same drill with this Jacobian matrix, the Hessian matrix. I'm just using the trust exact Newton method. It takes only about 13 iterations of 22, 23 to 24. Takes only about 14 functional evaluation. However, as the total executional time is a little bit higher, but this depends on how my starting solution is. But since all these problems are using the same starting solution, so this does indicate we spend a little bit more time on calculate the factorization of the Hessian function, Hessian inverse basically. And therefore it is a little bit time consuming. However, the number of iteration is much less. So this pretty much concludes some of the popular method for solving large scale method is the limited memory BFGS method with box constraint, and Newton's conjugate gradient methods, and trust region Newton's conjugate gradient method, and this is trust region near exact algorithm for medium-sized problem. All right, so these are some of the more detail, and also we show you how to using the Jacobian information and the Hessian information for solving, helping the algorithm. Before Last lecture period, we only introduced some of the unconstrained optimization problem, but we never discussed quite a bit in depth how to using Jacobian information, how to using Hessian information, how to using a so-called Hessian product information. Okay, next subject we have is talking about constraint optimization algorithm with the multivariate function using the minimum. To dealing with constraint, actually, the SciPy only gives you, SciPy.optimize library only gives you 3 different choices. One is the trust region constraint problem algorithm. The other one is the successive linear least square quadratic programming problem. And the other is the Cobila is a successive linear approximation algorithm. They require constraint to be defined a slightly different structure. For example, we mentioned that before. The trust region conjugate constraint problem algorithm required the constraint can be defined as actually is not required. The constraint can be defined. It's not required, basically. I will show you why. The trust region constraint algorithm, the constraint can be defined as a sequence of objects of so-called linear constraint and nonlinear constraint. However, the successive least square quadratic programming algorithm and the Cobila, so-called linear approximation algorithm, they require their constraint to be defined as a sequence of a dictionary and with a key type function and Jacobian function. Okay, so we're going to illustrate that. As an example, we can give you an example, the same thing, the minimization problems, objective function is a Rosenblock function. However, I put it in several different type of constraint. Okay, first is a linear constraint, x0, x0 plus 2x1 less than or equal to 1. Second constraint and third constraints are nonlinear constraint. Okay, and the fourth constraint also is a linear constraint. Then I have a bounds on each one of the variable. So x1 is between 0 and 1, x2 is between negative 0.5 to 2. Okay, so this problem has a unique solution. It's 0.4149. The other x1 equals to 0.17. So here we'll show you various ways to define the constraint in this test problem. So first we introduce how to define bounds on the variables and basically import SciPy.optimize, import so-called bounds. Bounds can be defined by this bounds function with couple tuples for E1 for each one of the pairs of variable. As a lower bound, upper bound, lower bound for x1, x2, upper bound for x1 and x2. So if you have 5 variables and the first tuple will have 5 elements in a list. The second, this is upper bound. If you have 5 variables, then you have 5 elements in this list. Second, we define a so-called linear constraint. Linear constraint, like we have 2 of them, the first one and the fourth one. Define a linear constraint, we can use forming the so-called constraint matrix. the first constraint is x0 plus 2x1 less than or equal to 2. The second constraint is a linear constraint of 2x1 plus 2x0 plus x1 equals to 1. So we can define the lower and upper bound for this constraint. If you look at this, so I have 1, 2, 2, 1 times x0, x1 is between, for the first constraint, there's no lower limit, so it's negative infinity, but the upper bound is 1. For the second constraint, since it's an equality constraint, so it's lower bound and upper bound both equals to 1. So now, after we transform into this matrix form, A times X is between certain upper and lower bound, so we can define using a linear constraint method. The linear constraint we sort of talked about a little bit before. The linear constraint will give a matrix, so it's 1, 2, 2, 1, and then give you a lower bound, then it's upper bound. Negative infinity and 1. The upper bound is 1 and 1. So here we trying to illustrate how we define these two nonlinear constraints, the second constraint and the third constraint, okay? Right here. So this constraint basically as x squared plus x1, x0 squared plus x1 is less than or equal to 1, x0 squared minus x1 is less than or equal to 1. So therefore, we can write their Jacobian matrix, and it's actually equals to 2x0, 1, and 2x0, 1. So we take the first derivative with respect to x0 and x1. So we have a Jacobian matrix. Also, we can take a Hessian matrix. Hessian matrix is V naught times 2, 0, 0, and V1 times 2, 0, 0. Okay. So, okay. Then we can see this, how do we program it. First, we define the so-called the constraint function itself, the Jacobians of the constraint function, since the constraint is a vector, so the Jacobian will be a matrix. And second, we define what is the so-called Hessian of the constraint. And we can define the following nonlinear constraint using the constraint function, upper and lower bound for that constraint function, okay? Jacobian functions and Hessian function. Okay. Alternatively, we can possibly define the Hessian of the matrix as a sparse matrix. I'm going to skip this part because it requires other explanation. First, defining the so-called nonlinear constraint as sparse or nonlinear function in a sparse as well. And sometimes, and our objective function of the constraints is Hessian is difficult to compute, or there's probably no explicit form, or is computationally infeasible. So therefore, we meant using a so-called Hessian update strategy provided by SciPy.optimize. Currently, the update strategy has a BFGS method and SR1 method, basically using 2-point finite differences. Okay, so the same nonlinear constraint we can using the Jacobian information, and the Hessian, I'm just saying, using the BFGS algorithm to approximate. Also, the Hessian can be approximated by linear in using a two-point method. Basically, it's the SR1 update. Same thing, the Jacobian can be also using the two-point update as a default, and if the Jacobian calculation is somehow difficult. Once I show you different options to define the linear constraint and nonlinear constraint, we were ready to using the minimize library function to solve this problem with the constraint. Fairly straightforward, since we're defining different objects using the trust region constraint algorithm. So the Jacobian and the Hessian for the objective function. Then for the constraint, I have a linear constraint and nonlinear constraint. I define them. And I have also the bounds on the variable as well. So we can solve this problem, okay, with give you a solution, 0.4149 and 0.17 are the solution, okay, and the function, objective function equals to 0.3427. It takes about 12 iterations, only 8 different functional evaluation, okay, 8 of Jacobian evaluation, and so on. And here I didn't give any tolerances on the constraint as well for the equality and inequality constraint. And this is the trust region radius. So we practically didn't use any of the trust region since we probably don't need it for this case. Okay, again, we're using the so-called Hessian vector product using, in this case, we're using Hessian product. To solve these problems was more complicated using only half of the time, okay, half of the time for using directly the Hessian. So for these more complicated problems, this a little bit might be so-called using Hessian product might be a little bit more efficient in this case. Okay. Second, we're going to be using a so-called SR1 method for the Hessian approximation for the objectives as well. Okay. As taking a slightly less execution time as well, taking only 12 iterations, 0 Hessian information evaluated instead of 8 of them, so that's why the saving coming from, and so on and so forth. I also give you these 2 references right here for these methods. The last one we're going to talk about is the so-called sequential least square programming algorithm, which my personal view is one of the most reliable method and stable method to solving nonlinear programming problem with constraint. But however, using this so-called SLSQP method, we could successfully quadratic approximation and solving as a least square problem. And their constraint has to be defined in a dictionary format. So what is that? So we'll show you example how to define the inequality constraint and the equality constraint in that case. This method, this constraint using dictionary tuple, and it's a little bit easier in my view, but however for some user not really familiar with this so-called Python dictionary dictionary definition is a little bit more involved, but let me explain, and you will see it's not that difficult. So for inequality constraint, we have, let's see how many inequality constraint we have. Inequality constraint, we have a first constraint, second constraint, third constraint, and we'll have one equality constraint. This is the fourth one. So let's see how we define these. And using the dictionary method, it doesn't matter with the linear or nonlinear constraint. We can all define it in a functional format. So for the inequality constraint, I'm using this. First, this is a type. Type, you see here we have nothing. We call it, we can call it constraint, constraint 1 or something, but don't need it. And we'll show you, here shows is an inequality constraint, and this is the function, and using the lambda function, we call it implicit function lambda with a variable of x. So here we have three inequality constraint. The first one is 1 minus x0 minus 2 times x1 greater than or equal to 0. Remember, we talked about before these so-called lambda function. As always, the dictionary function is always non-negative, greater than or equal to 0, instead of less than equal to 0. Second constraint, I have 1 minus x0 squared minus x1 is greater than or equal to 0. The third constraint was 1 minus x0 squared plus x1 greater than or equal to 0. And here I have is Jacobian for each one of the constraint. Okay. And the second constraint, we'll call it equality constraint. Type is empty, okay, blank. And it is an equality constraint. I have one constraint function also. One constraint function is an implicit lambda function with a variable of x, and this is one single constraint. Okay. And this is corresponding Jacobians 2 and 1 as a vector. So you can see that we have a type of the, and then inequality is inequality constraint, and then we have a function is function definition, and is Jacobian information. Same thing. This type is equality constraint, and function and the Jacobian. With that, I can start solving the problem. Solving the problem with initial guess of 0.50 on these. Okay. So here we're using successive linear least square quadratic programming algorithm, using both the equality constraint and the inequality constraint put in the list. Okay. Here we have the tolerance for the objective function value and the bounds on the variables as well. So we solve this problem. Only takes about 26 milliseconds, about a half of a previous so-called trust region constraint method. So therefore, this is algorithm slightly more efficient than the previous trust region method. It only takes about 4 iterations. Functional evaluation using 5 functional evaluation. So 4 iteration, we reach the optimal. And only using 4 Jacobian evaluation, and this is the solution. I'll give it to you. Well, this is a demonstration on 2 different type of constraint optimization algorithm. One is this so-called sequential least square programming problem, okay, quadratic programming problem, okay, and the other one is using the trust region Newton's method with a constraint. So you can compare and pick and choose which algorithm you want, and we show you different ways to define the linear constraint and the nonlinear constraint. We can using a specific linear constraint function, okay, from the SciPy.optimize library, or we can use the so-called dictionary definition method. Again, here we separate inequality constraint and equality constraint using the type, okay, and function we're using lambda with x. And actually, we don't have to using implicit function lambda. We can define a constraint myself, and then we're using directly here to referring to the function. We can define our user function and do it that way. Okay. All right, we pretty much finished this notebook. Nonlinear programming minimization part 3, and we will start going to part 4. I wanted to introduce some global optimization algorithm using evolutionary algorithm. But before that, I decided to add a couple new notebook using the so-called modern first-order optimization algorithm we introduced in our lecture, referring to the momentum algorithm, the so-called RMS probe algorithm, and what is it, Alda Delta and Adams algorithm. So we will show you some of those algorithms, how we actually implement it from scratch. And I also will like to show you how they can be applied in the machine learning arenas, and how some of the machine learning example using these algorithms to adjust their neurons weight. So here, I'm just going to stop right here, and so we see you in the next lecture period about modern optimization algorithm and their application in machine learning. We'll see you in the next lecture.